In today's video, we are going to do a lesson about how to find the limiting reactant using a method called the cycles calculation. So there are multiple ways you can find the limiting reactant in a chemical equation, but I really like the cycles method as I think it's really efficient and I think it's an easier way to do a limiting reactant calculation. After we do our summary lesson, we'll look at a sample question from one of the older AP chemistry exams and we'll solve that question together. So the cycles method, what is it? Well, before we even jump into that, let's remind ourselves that when I have a balanced chemical equation like I'm showing here, what this means is that if I have exactly 4 moles of aluminum and I reacted it exactly with 3 moles of oxygen, they're both limiting or they're both consuming each other fully to create exactly 2 moles of product. However, I don't always have this exact ideal mole ratio that I see in the balanced equation. So let's pretend let's say I'm going to give you some data, okay? So let's pretend I have 0.100 moles of aluminum, and let's say I also have 0.100 moles of oxygen. So I have the same amount of reactant, okay? So when I look at these values, I can see that these mole values, they don't react in a 4:3 ratio. So that means that one of them will be limiting. One of them I'm just going to have enough of to create product, and the other reactant will be excess, or I'll have too much of it, I'll have some leftover. So how does this cycles calculation work? So the cycles will equal the actual moles divided by the stoichiometric coefficient. So that's just a very fancy way to say that this balanced equation or the balanced ratio I see on the top. So I'll just call it the stoic coefficient. And okay, I'll just rewrite the formula here because I'm going to calculate this once for aluminum and I'll calculate it again for oxygen. So actual mole divided by stoichiometric coefficient. So for aluminum, my actual mole, by the way, the actual mole is this. That's what although I just made it up, that's what I would actually have, let's say, in this situation. So for aluminum, I've got an actual mole value of 0.1. My coefficient is 4 moles. Moles cancels out, and I'll get a cycles of 0.025x or times. And what this actually means is that if I have this much aluminum, I would be able to run the reaction this many times. So I'm going to try to do the same thing with the oxygen and compare these values. So for my oxygen cycles, it's going to be 0.1 mole over 3 mole. So remember, actual over stoichiometric coefficient, that will give me 0.033 repeated times. So if I have this much oxygen, I will be able to run the reaction this many times. So if you interpret these cycles data, how do I know which one's limiting? So it's always going to be the smaller number, okay? So for example, this aluminum, this is a smaller number of cycles. So what this means is that the aluminum, this actually will run out first. Okay, so the smaller cycles will always run out first, and the smaller cycles will always be your limiting reactant. So therefore, in this example that I just made up, aluminum is my limiting reactant, and oxygen is my excess reactant. Okay, so if I was to, now it's not asking me to, or we're not going to look at this right now, but if I was to figure out how much product do I have, remember that it's always the limiting reactant, the aluminum in this case, that will determine how much product I formed. So we could look at that in another video if you're interested. So let's go and actually look at a sample question. Like I said, this comes from the 2016 AP Chemistry free response. It's posted on their website if you want to check out the rest of it. So I'm given this chemical equation, I rewrote it on the bottom, and I basically am being asked, based on the information above, identify the limiting reactant, and then justify our answer using calculations. So I'm going to do a cycles calculation, okay, what I just showed you. So before I can do that, I need to figure out, let's look at my first reactant here, sodium bicarbonate. I'm given the grams. So actually, if I scroll back up, if you look at my cycles calculation, I need to divide mole over mole, or actual moles divided by the coefficient. So I'm going to need to change grams of the reactant into mole. And by the way, there's a mole formula, moles equals mass over molar mass. So I'm going to do that, and I'll just show my work here. So the mass of the compound is 2.24 grams. If you use your data table, periodic table, the molar mass is 84.0 grams per mole. And that will give me a mole value of 0.0267 mole. My other reactant, again, I'm going to need to figure out how much do I have in mole. And I have a volume and I have a concentration. So there's another mole formula I can use, and this is an aqueous reactant. So I know here that moles equals concentration times volume, or N equals C times V. So the mole for this one is going to be the concentration is 0.875 moles per liter. Okay, now be careful. The volume here, we have to change it to liters, okay? So 60 milliliters. If we change to liters, we move this 1, 2, 3 to the left. So this becomes 0.060 liters, okay? Actually, 0.060 liters. So liters will cancel out, and my answer will be in mole. And I'll have a mole value here of 0.0525. Okay, now we're going to change this to cycles to determine which one is our limiting reactant. Now notice in this balanced equation, it's already balanced for me, okay? You can count the atoms in your head to double check, but pretty much it's a 1-to-1 mole ratio, so everything is 1, okay? All of the balanced coefficients here, these are all 1s, okay? Although they're not written down. So technically, I don't have to write this down, but I will. So I'm going to say that the cycles of my first reactant is, so remember that I don't have enough space to write the formula again. So scroll up here to remember that this is the formula. Cycles equals actual mole over the coefficient in the equation. So for this first reactant, it'll be 0.0267 mole divided by 1 mole, which will just give me 0.0267 times. So if I have this much moles of my sodium bicarbonate, I will be able to run the reaction this many times. Well, what about the aqueous reactant? It'll be 0.0525 mole divided by 1. And this will give me cycles of 0.0525x, or times. So again, what did I say before? We have to look for the smaller number, the smaller cycles. So as you can see, the sodium bicarbonate, this is a smaller number than my cycles over here. So my sodium bicarbonate will run out first. So I'm going to say, therefore, NaHCO3 is my limiting reactant, as it will run out first, shown in my cycles calculation, okay? As seen by smaller cycles. I hope you like this method of solving the limiting reactant. I just think it's really, just a really, like I said, efficient, kind of quick and easy method to do so. And yeah, if you want to see another sample question, please let me know. And if you have any questions about this method or a problem like this, please also leave a question in the comment section. Thank you very much for watching, and have a great day.